Ladies and gentlemen, please welcome to the stage a representative from Phasecraft.
Hello, everybody. My name is Steve Flammia. I work with Phasecraft here at the U.S. office. I'm also a professor at Virginia Tech, and I head the Center for Quantum Computing and Quantum Architecture there. Today, I'm going to tell you about some work I've been doing with Phasecraft about quantum optimization for securing tomorrow's energy grid. So let me tell you a little bit about Phasecraft first. Phasecraft are world leaders in quantum algorithm development. Phasecraft was started by three professors, Toby Cubitt, Ashley Montanaro, and John Morton in the UK several years ago. They recently expanded to the US office, and they tapped me to help staff and run that US office. We're now up to 30 people just on the research and development side between London, Bristol, and Washington, DC. We run quantum algorithms, which means that's a software side of things. But in order to run those quantum algorithms, Phasecraft partners with all of the world's leading hardware providers for quantum computers. So that includes Google, IBM, Quantinuum, Quera, as well as others. So let me tell you a little bit about what Phasecraft envisions for application spaces for quantum computing. There's two main application spaces where we expect to deliver quantum advantage above and beyond what is possible with present-day high-performance computers or AI or just any form of conventional computation. So those two main areas are, one, simulation of quantum systems. So these are application domains where we expect to see exponential speedups for modeling properties of physical systems where quantum mechanics plays a key role. Some examples of this are batteries, solar cells, chemicals, or pharmaceuticals. We partner with Johnson Matthey, Oxford PV, Wellcome Leap, or any partner where developing these types of materials or systems is of interest. These are key applications in basically every sector of the economy. And we need to be able to do this because the speedups provided by quantum devices for solving these problems are going to be essential for transitioning from a world where we simply discover properties of the world around us to a world where we can actually design properties of the world around us. So to pick an example, we don't really understand why, when they discovered Tylenol, it was exactly that, it was a discovery. It wasn't by design. That's just one example. So many discoveries in material science or pharmaceuticals are of this form where through trial and error, we discover we want to be in a world where we can actually design, and we'll need quantum computers in order to do that. The other main application space that Phasecraft is interested in is optimization of complex systems. This also has an extremely broad application space with applications in finance, logistics, and what I will touch on most today, energy networks. Phasecraft partners with BT, the Department for Energy Security at Net Zero, and NESO. Okay. So to touch on energy grids, energy grids are a huge and important chunk of the economy. So these are just some headlines from the last few months that show the size and the scale of the issues that are faced by trying to have robust energy networks that are secure in multiple senses of the word secure. So secure could mean robust when there are things like fires. So you can see here California power outages swell to 400,000 as fires multiply. So these are natural disasters, earthquakes, tornadoes, hurricanes, fires that can threaten power grids, but also robust to malicious actors. You can imagine people, malicious actors trying to actively damage power grids. And the scale of the economic impact of the energy infrastructure is, you can see on these slides, billions or trillions of dollars. So one of the goals of Phasecraft is to optimize energy grids, because an optimized energy grid is a secure energy grid. Okay, so what does an energy grid look like? Well, I can't just show you an entire energy grid, but I can show you a schematic representation of an energy grid, and it's quite complicated. So here you see a diagram where there's a bunch of wires, there's a bunch of symbols that represent various power loads or transmission areas that carry various weights that say how much power they can transmit from node A to node B. And whenever anybody models one of these networks, they always abstract away the details. So they're not interested in, the specific, like the address of this specific power station. Rather, they're just interested in the coarse sort of topological features of this network and things like, what type of power station is it? So here schematically represented as, red or a blue node. And then maybe some abstract edges that describe some of the properties that we're most interested in, like the power capacity transmission from node A to node B. Okay, and this representation is called a graph or a network. Now, many problems that are of interest can be reduced to this level of modeling, which you can see is a great simplification. If you try to solve these problems to optimality, in general, this will take an exponential amount of resources, okay? So if you have 100 nodes in your power station, that means that the number of resources scales like 2 to the 100 power, or something like 10 to the 100 power. That's one with like 100 zeros after it. This is a very big number. This is very, very hard. No amount of compute anywhere in this hall from any of the brilliant people that we see around us is going to solve problems that take that much time or resources. Okay, can we do better? Well, we can do somewhat better if we use quantum optimization, and that's what the rest of this talk is about. So to give you examples of how problems in energy network optimization can be mapped onto problems in what's called graph theory, where we use this graph representation, I'll just pick two. One of them is the maximum power section problem. I have 4 examples on here, actually. Another one is the problem of min-balanced cut. Intentional islanding maps directly onto this problem of min-balanced cut. So what is intentional islanding? For example, you have some nodes that are threatened or are not working or something, and so you want to isolate them in a way which optimizes the rest of the grid, conditioned on having dropped out a few of the nodes from your grid. So basically power rerouting in some optimized way. So other problems like PMU placement reduces to vertex cover, minimum vertex cover. Optimizing your backup power sources, which is clearly important, reduces to maximum independent set. So if we can solve these graph theoretic optimization problems, then we can do really tremendous work for optimizing and securing energy grids. Okay. Right, so we would like to do this not 20 years from now, but today. So what is the state of the art of quantum computers? Well, unfortunately, the state of the art of quantum computers is that, despite tremendous efforts by brilliant people, they're still relatively small scale and relatively prone to errors. So here is an example of arguably the world's best performing quantum device that is being currently manufactured. So Google's 105 qubit Willow chip. So you can see from the ad that it advertises this as a major quantum milestone, and it was indeed a major quantum milestone when they built this chip. But 105 qubits is unfortunately, on the scale of things, rather small. By comparison, so a qubit is a quantum bit, 1 bit of quantum information. Anybody's mobile phone that they have in their pocket right now carries a billion or more many bits of memory, for example, and computing power in some sense. So how are we going to get anything useful from such small devices? Especially when, as I mentioned, they're still error prone at the moment, present day devices. So the solution is to do quantum enhanced optimization. Okay, this is our proposed solution. So many classical optimization algorithms are based on starting with an initial random solution to the problem and then doing some kind of search based on that solution. So you guess an answer and then you refine or polish that answer to try to improve it. So some ways that you might improve it are, it could be anything. So on these bullet points, I say local search algorithms, genetic algorithms, simulated annealing. It could be your favorite AI application as well. It could be anything to try to improve an initial guess of a solution. This isn't a straw man. This is really how these things are solved. Okay. So we start with this hard optimization problem. We guess an answer and then we refine it using our best conventional techniques. So then our goal is to replace this choice of an initial random guess with the output of a quantum algorithm that's being run on a near-term or present-day quantum device, quantum computer, okay? So doing so will hopefully give the classical side of the algorithm, the conventional computing, a warm start rather than a cold start for the polishing steps. And then we hope to improve these solutions. And I will show you data demonstrating this in a little bit. So this is the workflow here. Hard optimization problem. We run a quantum algorithm that generates noisy data. We take these noisy data. Maybe we do a little bit of pre-processing on that. And then we use that as a warm start to a classical optimizer. And together, the quantum coprocessor with the classical optimizer will accelerate the answer to the problem. Okay? And crucially, we're running, the plan is running this on present-day devices. Okay. So we can go into an example here from one of my earlier slides, max cut. So max cut, we recall, corresponds to this problem of maximum power section. So for those of you who like math, you can see the optimization problem here in the upper right that corresponds to maximum cut. We want to optimize that function. Okay. So this isn't just for solving maximum power section, by the way. I tried to emphasize this before, but I think it bears repeating. There are applications in clustering, load balancing, network partitioning, for example, for any kind of network. Could be a wireless network, for example. Image segmentation. So it's beyond just power grids, the scope of solving this optimization problem. And again, to emphasize this point, it is exponentially hard to solve such a problem exactly, okay? To show you what the scales are in practice, if you wanted to solve such a problem exactly on 100 nodes, that's about the state of the art that you could do with conventional computers, even HPC. If you're not interested in solving it exactly, but just getting a pretty good solution, then you can apply these heuristics about local search and optimizing and things, and you can get decent solutions on 1,000 nodes, okay? And our goal, again, is to use a quantum coprocessor with this quantum enhanced optimization to speed up these heuristics and improve the quality of the solution. Okay, Phasecraft has implemented a full software stack for quantum enhanced optimization. So you can see a sort of workflow for this software stack where we first partition the input graph into a collection of subgraphs. These subgraphs are small enough that they can fit on today's quantum hardware. Then we calculate cuts using a specific quantum algorithm called QAOA. It's not important what it is or what it does, but we use a quantum algorithm to get initial cuts for each of these smaller subgraphs, and then we reconstruct an overall cut from cuts from the subgraphs and use that as a warm start for the classical optimizer, okay? So this is a video of how this works. So on a very small example using simulated data. So we first take an input network and we partition it into some subgraphs. We need to be able to fit this onto hardware which has very messy connectivity diagrams. So it's not that the hardware directly corresponds to the topology of the network that we're studying. We have to actually analyze that and then map onto that hardware. We have to compile quantum circuits that will then run on that hardware using the native gates available on that hardware, working with one of these hardware providers. We have to compile this down into specific quantum circuits with specific quantum instruction sets. And then we have to schedule these quantum circuits to run in the cloud, or we transmit these in the cloud to a quantum hardware provider, such as one of our partners, IBM, Google, Quera, Quantinuum, etc. They run that quantum algorithm and send us the data back again from the results of those quantum computations. Now, those results are, unfortunately, because of the present state of play of quantum computing, a little bit noisy. So we have to run an error mitigation layer. We improve those results with a little bit of post-processing, and then we get a collection of initial cuts, and we use those initial cuts now as a warm start. So now we hand these warm starts to a classical optimizer, and we start counting solutions that we get to this optimization problem. So we run this some number of times, and we count the number of times that we get an optimal solution. And you can see when all of the computation is done, we've got about twice as many solutions running the quantum coprocessor together with the classical optimization step compared to running just the classical optimization step in isolation. Okay, so that was a simulation. That was just some code that was simulating what's actually happening. But on this slide is actual data from an IBM quantum device, okay? So we ran two quantum algorithms, one corresponding to this max cut problem, another one, the one on the right, is maximum independent set. I'll just focus on the one on the left for time reasons. So for the three different colors of lines that you see here correspond to three different families of optimization problems that we tested. And you can see that in every case, there's a quantum speed up factor by running the quantum coprocessor together with the classical optimizer. Okay? In some cases, without error mitigation, the speed up factor is relatively modest. But with a little bit of error mitigation, running them in tandem, we get speed ups up to 1,000 versus the baseline compared to purely running it on a classical, running only a classical optimizer. We get speed ups of order 1,000 running this on problem instances of size 30 nodes. Now, of course, I mentioned we can solve things exactly using conventional hardware on instances of up to 100 nodes. So this is not providing present-day economic advantage for running this, but it illustrates the promise of this. There's a real speed up using present-day hardware today. If you want to try this yourself, so there's a Phasecraft booth right down the middle there. You can go check out the booth. You can also go to the Phasecraft website, optimization.phasecraft.io. On there, there's a web tool for demonstrating how this works in practice. So you can create your own node. You can give it some edge weights or something that correspond to whatever you like. And it will do a simulation. It doesn't run it on hardware, not on the website at least. And it will do a simulation and tell you what an expected Q factor is, or a quantum speed up, if you were to use our quantum algorithms together with quantum hardware as a coprocessor together with conventional compute. So what does the future look like? So let me just recap briefly before saying that, what we've done. So we can take hard optimization problems, take a quantum algorithm that generates noisy data, so today's quantum hardware, and run it in tandem with a classical optimizer as a coprocessor, and the result is an accelerated answer. Okay, we get accelerated or improved answers. So I mentioned the applications specifically to energy grid optimization or energy grid security, but also applications to finance, logistics as well, and also other applications besides max cut. So for energy networks, for example, load balancing or fault isolation, this immediately applies to problems like facility location in logistics, or problems in portfolio optimization in finance. So the next step, which we're working on currently, is to expand this to a larger class of optimization problems that are harder than the ones that I've just described. So we're doing this by developing quantum algorithms for something called mixed integer linear programming. If you know, you know. Hard optimization problems in this class can be solved with algorithms we're developing by combining quantum algorithms for warm starts together with a classical optimizer. That's that first layer that you see at the top. And then running them as a subroutine, and then feeding those as as warm starts to an optimizing classical layer again. Okay? And then again, we expect accelerated answers for this larger class of problems using this enhanced algorithm. The types of applications that we expect to see with this class of optimization algorithms using Phasecraft algorithms and quantum coprocessors is more complex portfolio optimizations in finance, shipping scheduling in logistics, and problems like unit commitment in energy networks. So to summarize, we can use quantum enhanced optimization to speed up classical algorithms for solving highly computationally challenging problems. These have applications in specifically energy networks, but also in logistics or in finance. We're working with partners to develop these applications and push towards quantum advantage today, not 20 years from now, but today or tomorrow. So please get in touch with us if you'd like to learn more. There's a booth here, and I'm going to stick around for questions over in the back at the end of this talk. Thank you for your attention.